In this video, we'll cover fireflows, flushing, and hydrant analysis. We'll start by analyzing fireflows with specified minimum pressure. First, we need to go to the Analyze menu, and then the Analysis Setup menu. Next, we'll press the radio button for fireflow and hydrant analysis. Now, let's talk about the features available for use with the analysis. First is the global demand factor. This varies the demands in your model. So if I put a factor of 2.0 in this field, the model demands are doubled. Note that the global demand factor is the only way to affect model demands. Other features, such as demand patterns and node changes, are ignored when running a fireflow and hydrant analysis. You could also check this box, which would remove all the demands in the model. Although normally fireflow demands and domestic demands apply at the same time. Here we can add a fireflow report title. Next, we'll choose what type of analysis we want to perform using this drop-down menu. The first option is to analyze a fireflow with a specified minimum pressure. This is the minimum pressure allowed throughout the system, which is usually 20 psi, but is user-defined in this box. To clarify, the flow we're specifying is a pumped flow. It's not a flow with a hydrant open, such as in this image. Rather, it's the flow we would obtain if we used a pumper truck to draw water out of the system until the system achieves the user-specified value, which in this example is 20 psi. The other two options are flush flows, and we'll talk about those later in the video. Next, we can define a static pressure limit. Likely, we've already told the program that we want the rest of the system to stay at or above 20 psi when running our hydrant analysis. However, there are often nodes in the system that start below 20 psi, usually on the intake side of a pump, for example in a clear well. We can tell the program to ignore nodes whose pressure begins below a certain value, which is specified here. Next, we need to tell the program which nodes to include in the analysis. We can specify only selected hydrants or all hydrants. However, if you don't have hydrants in your model, you can use junction nodes instead, either all of them or only specified junction nodes. Let's choose selected hydrants. Next, looking at the model, we see there are 9 hydrants. If I go into group edit mode, I could specify, say, 3 of the hydrants to run the analysis for, giving us results for only these 3 hydrants. And by results, I mean the fireflow at the specified minimum pressure, which is used for National Fire Protection Association hydrant color coding. However, one question that comes up is, are all 3 of these hydrants flowing simultaneously, or is the program analyzing each individually? And the answer is that the program is analyzing them individually. It turns one hydrant on, analyzes its flow, then turns it off and goes to the next one. Currently, the fireflow routine does not have a mechanism in place to flow multiple hydrants simultaneously. We would need to use blow-off nodes to accomplish that, which we'll talk about later on. So let's talk about the hydrant node itself. In the Hydrants Node Info window, we see, among other things, an elevation. The elevation allows you to account for the difference between the depth of the buried pipe and the height of the hydrant. So that's one reason to use hydrants as opposed to junction nodes. Also, we see these fields, the static pressure, the residual pressure, and the residual flow. These inputs are optional. They are normally derived from field tests, specifically fire hydrant flow tests. One good thing about entering these data points is that doing so allows the program to calculate a hydrant constant, which we'll talk about in a minute. These next 2 fields are the calculated static pressure and the calculated fireflow, which are determined by the program once we run the fireflow analysis. Let's go back to the Analysis Setup menu, and while we could run the analysis for the 3 hydrants we've selected, Instead, we'll click the radio button for all hydrants and then run the analysis. Going to the analysis report and then using the drop-down selector to select the hydrant analysis report, we see that the program has returned two different flow values. These are labeled Flow 1 and Flow 2. Here we see an explanation for these values. Flow 1 is the flow rate required to maintain the minimum specified pressure at the hydrant node itself, or at the junction node if we've specified junction nodes instead of hydrants. This, of course, uses the 20 psi value we entered earlier, but it's important to understand that it measures that value at the hydrant node itself, not anywhere else in the system. Flow 1 is the most important result for most of our users, but there's a caveat, which is that sometimes other nodes in the system will get down to the 20 psi minimum before the fire hydrant itself does. For example, if the hydrant is at the bottom of a hill and there is a nearby node on top of the hill, that nearby node would probably achieve 20 psi first. This doesn't happen universally, but when it does, we report the flow at which this occurs as Flow 2. Specifically, Flow 2 is the flow rate out of the hydrant when any other node in the system reaches 20 psi. In the report, we also provide the name of the node that reaches 20 psi before the hydrant in question does. There's also a third value we can calculate called Flow 3. Flow 3 accounts for losses between the hydrant and the fire department's pumper truck. Sometimes a fire department or a regulatory agency will want to know if there's going to be a break in suction in the hose on the inlet side of the pump at the fire truck. So Flow 3 was created to account for these losses, including losses at the hydrant and within the hose connected to the fire truck. Sometimes people want to see this Flow 3 data point, and sometimes not. If you do, you'll need to check the Calculate Suction Pressure at Fire Pump checkbox. Additionally, to calculate Flow 3, you'll need two numbers. The first is the default hydrant and hose constant. This accounts for the pressure drop between the hydrant and the pumper truck. We can calculate this using the Hydrant, Hose, and Nozzle Constant tool. We'll need to input the hose diameter, the hose length, and the hose friction factor, which defaults to 0.02 if no other value is entered, which we can see by mousing over this part of the menu. Next, we'll enter the diameter of the hydrant opening, as well as the hydrant's coefficient of discharge, which defaults to 0.62 if no other value is entered, which we can see by mousing over this part of the menu. Now the tool will calculate a combined hydrant and hose constant. Let's input that value into the menu. The second number needed for the Flow 3 analysis is the minimum suction pressure needed at the fire truck's pump inlet to maintain suction. 5 psi is a common value. Now we'll analyze the model so we can also see the Flow 3 values. However, we have added the option to skip Flow 3 at the request of our users. The reason this request was made is that the hydrant analysis report gives all three values, Flow 1, Flow 2, and Flow 3, but outputs the flow capacity of the hydrant as the lowest of the three values. The flow capacity is what's used to determine the NFPA color coding for the hydrant, and also is reported in the map area as the calculated fire flow. Thus, if you don't want to run Flow 3, then uncheck this checkbox, which turns it off. To summarize, Flow 1 is the flow when the pressure at the hydrant reaches 20 psi. Flow 2 is the flow at the hydrant when the pressure anywhere in the system reaches 20 psi. And flow 3 is the flow through the hose connecting the fire hydrant to the fire truck that will maintain a value of 5 psi at the fire truck's pump inlet in order to maintain unbroken suction. And the flow capacity is the lowest of these three values. Another note about a Fireflow with specified minimum pressure. We don't need a hydrant constant if all we are analyzing is flow 1 and flow 2. This is because these are both pumped flows, and the software is going to draw enough flow through each hydrant to bring its pressure down to 20 psi, regardless of whether the opening at the hydrant is smooth or rough. The exception is flow 3. If you are analyzing flow 3, you need a combined hydrant and hose constant. As a final note on using labels to see your results for Fireflow and hydrant analysis, as stated, the flow capacity is the lowest of the three flow values, and this is normally what's displayed in the map area. However, it doesn't have to be. Instead, we'll go to the label menu and on the node labels side, scroll down until we see Fireflow 1 and turn it on. And if we wish, we can turn off Fireflow, which, as we said, displays the flow capacity, so that we'll only see the Fireflow 1 results. An additional way to see our results in the map area is to display the NFPA color coding. You'll remember that the flow capacity is translated to one of the NFPA color codes within the analysis report. These color codes can be displayed in the map area by first going to the Appearance tab, and then the Node Contours Emphasis menu, and then by clicking on NFPA Hydrant Color Coding. Returning to the map area, we see the color codes overlaid on the hydrant icons, along with a key. Now let's go back to our label menu. Let's turn off Static Pressure and Fireflow 1. Now, if we scroll about halfway up the list, we'll see Static Pressure, Residual Pressure, and Residual Flow, and we'll turn these on instead. Now we can see by looking in the map area that these are the inputs shown in the Node Info window for data collected during a field test, specifically a fire hydrant flow test. The data associated with a hydrant can be plotted on a graph. First, we need to select one or more hydrants. In this case, we have hydrant H4 already selected, so let's call up the graph for that hydrant. To do this, we'll click on the Devices tab, then on Hydrant Graphs. It's important to differentiate between the two different types of data displayed, however. Under Graph Type, the Test Data radio button is pressed by default. Thus, we are seeing the results of our fire hydrant flow test on the graph. However, we could press the radio button for analysis data, in which case we'd see the results returned by the model. If we wish to see the plots for more hydrants, we can make sure we are in group mode so we can select 2 additional ones. Now, returning to our graph, we see the results for all 3 hydrants. The next option in our drop-down list is called Hydrant Flow, no hose attached. This is an unpumped flow. So, it's the flow used for flushing the hydrant, that is to say, when a hydrant is flowing wide open. The model therefore determines a single residual pressure and residual flow value instead of calculating flow 1 or either of the other flow values we've talked about so far. First, we'll decide if we want to see the results for all hydrants or for only selected hydrants. Next, we'll select the analysis type. Last, we'll need a hydrant constant in order to calculate the residual pressure and residual flow. There are three ways to determine the hydrant constant. First, we can enter a default hydrant constant, possibly using a literature value. 120 is a common estimate when no other data are available. The next option is to use fire hydrant flow test data to calculate the hydrant constant. In order to do this, we check this box, Calculate Hydrant Constants, which allows us to go to the Node Info window for each hydrant where we have test data and enter the data in these fields, which allows the program to use this equation to calculate the hydrant constant, where Q is the residual flow and delta P is the pressure in the distribution system minus atmospheric pressure, and atmospheric pressure is, of course, 0, since the model reports gauge pressure. Alternately, if we already know the hydrant constant, or we want to calculate it ourselves, we can go to the Facility Analysis menu, click on Flushing Method, then press the radio button for Add a Hydrant Constant to the Node Info window, and now when we return to the Analysis Setup menu, we have the option to check this box, Use Input Hydrant Constants. Doing so adds a field to the Hydrant's Node Info window where we can enter the hydrant constant. If we don't already know it, we could calculate it using the equation we just saw, or alternately, we could use the hydrant, hose, and nozzle constant tool to determine it. Within the tool, we input the diameter of the hydrant's butt opening and the hydrant's unitless discharge coefficient. Then the tool calculates the hydrant constant. Note that if we don't enter a hydrant discharge coefficient, the tool defaults to a value of 0.62. We then enter the resulting value in the Node Info window. However, if we only enter it for some of our hydrants, the default hydrant constant will still be used for any hydrant where we didn't enter the hydrant constant manually. Now we can run the analysis, and the program will return a residual pressure and a residual flow. There won't be a flow 1, a flow 2, or a flow 3, just a residual pressure and a residual flow. In addition to going to the analysis report, our outputs are displayed in the map area using the labels for static pressure and Fireflow. Even though the label says Fireflow, and we are flushing a hydrant which is not the same thing, this is the convention used to display the residual flow for the flushing event. One last note about analyzing a hydrant flow with no hose attached. This is the scenario that best represents a hydrant located immediately adjacent to a large pressure supply, such as an overhead storage tank. If there is an overhead storage tank proximal to the hydrant, we don't use a Fireflow with specified minimum pressure to approximate the flow. Instead, we analyze it using a hydrant flow with no hose attached. This is because the flows generated by a Fireflow with specified minimum pressure analysis would be so high that the friction in the piping network between the overhead storage tank and the hydrant, as well as the friction in the fire hose, would become the dominant factors. Thus, a Fireflow analysis would overestimate the potential flow available. So in these situations, we use a hydrant flow, no hose attached, to simulate the maximum amount of delivery possible. A Fireflow with hose attached is used to analyze the scenario where a fire hose is connected directly to a hydrant, so there is no pumper truck present. First, we'll need to decide if we want to analyze all hydrants or a select group of hydrants. For this example, we'll analyze all hydrants. Then, we'll need to quantify 3 different types of friction losses in order to analyze the scenario. The first, as we've already seen, is for the friction at the hydrant opening, so we can use the hydrant constant values we've already calculated in an earlier part of this video. The second is the friction loss in the hose, and the third is the friction loss at the nozzle at the downstream end of the hose. Within this menu, both of these values are combined and entered into this field. Knowing the geometry of both the hose and the nozzle, we can calculate a combined value using the hydrant hose and nozzle constant tool. We'll need to enter the hose diameter, the hose length, and the hose friction factor, after which we'll enter the nozzle diameter and the nozzle discharge coefficient. Next, the tool will output a combined hose and nozzle constant. Again, if we don't enter a hose friction factor, the tool defaults to a value of 0.02. Also, if we don't enter a nozzle discharge coefficient, the software defaults to a value of 0.62. We then type the combined hose and nozzle constant into this field in the Analysis Setup menu. After analyzing, we see that the software again returns the flow rate and the residual pressure, which are displayed in the map area. We can also see these values within the analysis report. Next, we'll discuss using blow-off nozzles to simulate a multiple hydrant flush flow. First, we'll need to go to the Analysis Setup menu and click the radio button for KYPipe. We'll no longer be doing a Fireflow and hydrant analysis. Returning to the map area, we'll click on a pipe, click the Insert button, and create a blow-off nozzle with an elevation equal to that of the nearby hydrant. When created, blow-off nozzles are automatically turned on by default. So, if you don't want them flowing all the time, we suggest you turn them off initially until you're ready to run the simulation, and be certain to turn them back off when you're done using them. We'll add a second one here, with an elevation equal to that of the nearby junction node, and likewise we'll turn it off. Another input we need for our blow-off nozzles is a constant, which is the same as the hydrant constant discussed earlier, which in English units is the flow rate in GPM at a pressure drop of 1 psi. We'll go back to the Pipes tab and then the Tools menu, where we'll call up the Sprinkler Blow-off Constant tool, which works for hydrants as well as sprinklers and blow-off nozzles. We'll use the drop-down to select orifice diameter and input a 2-inch opening, and we'll accept the default unitless discharge coefficient, giving us a constant of 73.9. So we'll make the constant for each blow-off equal to 73.9. Now, we'd like to see what the system looks like before we open the blow-off nozzles. In order to see the flow rates under baseline conditions, we'll run the analysis using the Quick Analysis button. Next, we'll use the drop-down list to go to the Label menu and turn on Result A for pipes, then return to the map area. When we zoom in, we can see flow in the pipes that contain the blow-off nozzles. This flow is due to the demands entered at the junction nodes at the end of these pipes. Now let's open up the blow-off nozzles and rerun the analysis. We now see the higher flow rate in both these pipes. So, that summarizes how to simulate multiple hydrant flushing flows. It's done using blow-off nozzles along with a KYPipe analysis, and the blow-offs are kept closed when we're not using them. We can also use hydrant data to model a connection to a larger system as opposed to modeling the entire larger system. Let's say we want to prove that this subdivision can meet a certain minimum pressure. We set up scenarios like that using a node called a pressure supply, which we model using field test data from a fire hydrant that's as close as we can get to the connecting pipe to the main system. In theory, we could use a reservoir node to model the connection to the larger system, but the pressure available from a reservoir doesn't change with flow, whereas a pressure supply node operates on a characteristic curve, which is a much more realistic estimate of the pressure available with changing flow. There are two types of supply nodes, a rated pressure supply and a variable pressure supply. The rated pressure supply relies on an input static pressure, residual pressure, and residual flow value, and the software determines the shape of the curve. The variable pressure supply relies on multiple head flow data points to construct the curve. Let's model this area as a subdivision connected to a rated pressure supply. We'll delete this reservoir and replace the pump with a rated pressure supply node. We'll say that the fire hydrant we used for our flow test had a static pressure of 70 psi and a residual pressure of 65 psi at a flow of 600 GPM. Upon analysis, we can turn on our node labels and see that the pressures are in the 50s and 60s and thus acceptable throughout the system. Creating a variable pressure supply node is similar to a rated pressure supply, except we click on the ID field in order to enter head flow data points or pressure flow data points. This device ID, ID number 1, shows data for the pump. So we would need to create a new device ID for our rated pressure supply. In this menu, we would enter the data points in order of increasing flow. So the lowest flow would be on the first row, and the highest flow would be on the bottom row. While we can use blow-off nozzles to simulate flushing, we also have an application that's custom designed to create a flushing plan called the Flushing Planner. When we create a flushing plan using this feature, we first select the calculation method, then designate certain valves for closure to create a direction to the flow, and finally open up certain hydrants. We then analyze the system to see if we've attained a minimum velocity and make adjustments as needed. Let's say we want to flush this main line and this branch line. We'll start by inserting and closing valves on these branch lines here and here, and closing the valves on the lines to these tanks. Now we'll go to the Facility Analysis tab, then to the Flushing Method submenu, which allows us to choose a method to determine the flushing flow. Here we'll press the radio button to add a hydrant constant field to the node info window. Alternately, we could allow the software to calculate the hydrant constant from flow test data, or we could tell the software the flow we know we're going to attain at each hydrant during the flush. But for this example, we'll be inputting the hydrant constant directly. Now, we'll go back to the map area, and click on each of the hydrants will open up during the flush in order to input a hydrant constant. Next, we'll make sure we have both hydrants selected in group mode. Then click on the Analyze tab, followed by the Analysis Setup menu, where we'll make sure the radio button is pressed for Flushing Planner. Along with this analysis type, there are a couple of inputs, the most important of which is the display velocity. Likely, we already have in mind a velocity we want our pipes to exceed, so we'll type that in here. Let's say it's 4 feet per second. We can also input a flushing plan title. So now, let's run the analysis. It'll ask us if we want to create a new system, and we'll say yes. What this does is to overlay a flushed version of our model on top of our base model, which we can clear when we're done. So now we see our results. All pipes that are colored magenta are flushed at a velocity above 4 feet per second, and all pipes colored blue are flushed at or below 4 feet per second. So we would continue iteratively opening and closing different valves or hydrants until we achieved the best results possible. Finally, underneath the Facility Analysis tab, there is a flushing report. I'm just going to tell the software to include all pipes, and now this report is titled with the name of our flush plan. It lists the hydrants that we used and the flow that was achieved from them. It gives us a report of the pipes in the model and the velocity that they achieved. And last, it tells us which valves were turned off in order to achieve these flushing velocities, so we have that information in a handy report format. And once we're done with the flush plan, we'll clear it to return to the base model.